Hi, welcome to our presentation on the design of fabrication processes for 3D printed porous PEEK structures. We're Group 11. There are up to 132,000 knee and hip implant revision cases each year. Because bone grows in response to loading, a mismatch in material properties between bone and the implant can cause a loss of bone mass leading to implant loosening. This loosening is the primary cause of revision surgery. There's a need for improvement in the material choice due to that stress shielding and in the device structure to add porosity for integration. Current solutions include titanium and PEEK implants. While PEEK doesn't cause stress shielding, none of the current solutions offer easily customized porosity.
Our objective is to design a fabrication process for porous PEEK structures with a one-directional gradient. This figure shows the most important landmarks of a stress-strain curve in order to understand the mechanical properties to pursue investigation of PEEK structures. These include yield strength, the stress at which a specific amount of plastic deformation occurs; ultimate strength, the amount of maximum tensile, compressive, or shear stress that a material can sustain. These can be calculated by Young's modulus or modulus of elasticity, which is the ratio of the stress-strain acting on a material. Our constraints are based on client needs and ongoing research that include both geometries of gyroid and diamond structures, later discussed. Material is PEEK polyether ether ketone, a type of polymer, and manufacturing is 3D printing. We use PEEK because it has the most similar properties to bone. Other constraints include cost, legal, intellectual property, and safety.
Many requirements such as compressive yield stress, modulus of elasticity, permeability, and porosity were established to accurately mimic trabecular bone as well as existing implant technology. Printing accuracy and printability are also requirements that must be considered due to the process of additive manufacturing.
In order to create our structures, we've been utilizing what's known as triply periodic minimal surfaces.
Fused filament fabrication is a 3D printing method where the material is melted and extruded to create 3D objects. For our project, we are FFF printing at PEEK at 420 degrees C, so you have to keep in mind that it is much more finicky than the traditional PLA or ABS due to the higher temps.
The procedure we use to generate the sample begins with creating the mesh on a program called MathMod. This is how we determine the number of pores alongside one axis, which in turn determines pore size. We then import the object file MathMod generates into 3ds Max, which is where we can scale and manipulate the model, before exporting as an STL and importing it into Simplify 3D, where we can then choose the print settings and examine the print path. The program will generate the G-code, which will instruct the 3D printer on how it should move, and give us a preliminary view to see what the finished product should look like.
This schematic is showing a high-level overview. Starting on the left-hand side, these processes begin with defining an innovative approach by establishing relationships with software. The software platforms we use are highlighted in the middle of the schematic and follow procedures 1 through 4, as mentioned earlier. The right-hand side of the schematic shows the end of our final product, the fabrication of PEEK structures.
To verify permeability, we used a modified falling head test. We captured a video of the water flowing through our sample and used that to calculate the permeability. This table shows the permeability results. The smaller two pore sizes had acceptable permeability ranges. However, the water flowed too quickly through the larger pore sizes and those samples failed.
To measure the accuracy of the print, we utilized micro-CT and analyzed 12.0 to measure pore size. This is done by method of maximum sphere fitting, where the program finds the largest sphere that fits between 2 points in a scan. Porosity is also found using the same programs. Micro-CT will measure the solid volume of the scan, giving us the measured porosity, while Simplified 3D will measure the solid volume of the model before it's printed, giving us theoretical porosity. The results of the accuracy test shows us that our 400 and 500 nominal micron cubes are within acceptable ranges, while our 600 and 700 nominal micron cubes are bigger than we expected.
This table displays a trend where the porosity increases as the nominal pore size increases. However, the 600 micron sample doesn't follow this pattern since it was made prior to the standardization of the creation of the models for the cubes.
The impact of this project would be a precise control of porous PEEK structure through a combination of model design and 3D printing method, leading to a potential usage for enhanced drug release and bone modeling.
Overall, many samples still need to be printed, such as the diamond structure samples as well as a few miscellaneous gyroid structure samples. This estimates to 57 hours of printing still need to be done. Verification testing of the mechanical properties must also be conducted, including the creation of a testing fixture for the instron to minimize shear forces and optimal results, as well as a testing protocol for anisotropic compression testing that's needed to ensure uniform testing throughout. Optimally, shear testing would need to be conducted as well to calculate the modulus of rigidity. We'd like to thank our advisor Stephen Kurtz as well as Hannah and Dr. Sarver for assisting us throughout the project. We'd also like to thank the Drexel IRC and Exponent for providing lab space and materials to use.